Yes, hello, I'm Sören, and I'm a PhD student at the University of Bremen in Germany. And I would like to start off with a bit of motivation. So the goal of our work is to employ symbolic execution for testing embedded software. The majority of work, in my view, focuses really on this conventional desktop domain. And if you want to employ symbolic execution for testing embedded stuff, then there are several challenges that need to be addressed. And the first challenge that I would briefly like to discuss is that the embedded software ecosystem is much more heterogeneous than the software ecosystem for conventional devices. So in the conventional domain, you have operating systems like Linux, BSD, macOS, which are all conceptually very similar and all implement the POSIX standard to some degree, so they have similar input abstractions. And in the embedded software domain, you have a variety of different operating systems like Riot, FreeRTOS, Sapphire, which all differ in many core aspects. Some are multi-threaded, some are not multi-threaded. Some embedded systems are even programmed without any operating system at all. And so, yeah, the input abstractions differ, and you have in general a much more heterogeneous ecosystem. The other unique challenge, in my view, is that embedded software, of course, makes heavy use of peripherals and interacts with them on a very low abstraction level through memory mapped I/O, for example, or through interrupts. And the execution environment that you are using for your symbolic execution engine needs to support these interactions. And that raises, of course, the question, how do you model the behavior of these peripherals and how do you deal with these peripheral interactions on this low level? And in general, I think a central observation is that embedded software really interacts on a very low abstraction level with the machine on which it is running. So if you operate on a higher abstraction level, like if you're executing LLVM, then you need to deal with inline assembly somehow, which is, of course, very common in the embedded domain. And so to address these challenges, especially this big challenge regarding the dealing with peripheral interactions, there's a variety of prior work. A common approach is firmware rehosting, where you basically approximate peripheral behavior to some degree. For instance, just return unconstrained symbolic values for register reads and then make adjustments to the firmware to make it work with your approximated peripheral model. The other approach, which is in my view used more in the fuzzing domain, is hybrid emulation, where you execute your code in a QEMU simulator, for example, and code interacting heavily with peripherals is then forwarded to the real hardware, executed there, and after execution of this code, which interacts with peripherals, has finished, the entire state is put back into QEMU. And we want to employ instead accurate peripheral models. So we want to actually model the peripherals and have an accurate description of their behavior. And for this purpose, we employ hardware modeling. And I want to provide a bit of background on hardware modeling. So hardware can be modeled on different abstraction levels, for example, on the register transfer level, or on the circuit level, or on the transaction level. And depending on the level on which you are modeling your hardware, there's always a trade-off between accuracy and simulation performance. So, for example, on the circuit level, you can model hardware in a very accurate way. But if you try to simulate hardware modeled on the circuit level, then you get very bad simulation performance. And for symbolic execution, what is desired, of course, is a high simulation performance. And for this purpose, we use SystemC TLM, and SystemC operates on a very high abstraction level over here. And SystemC is essentially a modeling language based on C++. So it is a C++ library which extends the C++ programming language with facilities to model and describe hardware. And it operates on this transaction level where hardware is basically described based on a bus system, and you have hardware peripherals attached to a bus. And SystemC TLM allows you to describe the transactions that are exchanged over this bus and how the peripherals behave on certain transactions. And since SystemC offers such a high simulation speed, it is often used to create so-called virtual prototypes. And these virtual prototypes are widely used in both academia and industry. And virtual prototypes essentially provide you with an executable software model for an entire hardware platform. So virtual prototypes allow you to execute any binary code which targets a specific hardware platform. And as such, they also include SystemC TLM models for the provided peripherals by this hardware platform. So, for example, temperature sensors, UARTs, and so on. And as I said, virtual prototypes are an existing concept and basically their own entire body of research. And for this reason, there are various existing virtual prototypes. And our work is based on an open source virtual prototype for the RISC-V architecture, which is called RISC-V-VP. And RISC-V supports different RISC-V-based hardware platforms like the i5 Unmatched or the SI5551, which you can see on this slide. And this is exactly what we are using for our work. We are using this executable model for the SI5551, which is already part of RISC-V. But as I said, RISC-V only does concrete execution. And what we are interested in doing, of course, is symbolic execution. And this is where our main contribution comes in, which we refer to as the SymEx-VP. And SymEx-VP is essentially a combination of symbolic execution and virtual prototypes. And it integrates this existing RISC-V, which I mentioned on the previous slide, with KLEE. But contrary to normal vanilla standard KLEE, it does not execute LLVM-ER, but instead it operates on a lower abstraction level to address some of the challenges I mentioned on the first slide. And as such, it symbolically executes RISC-V machine code directly without any intermediate language. So RISC-V instructions, of course, take registers as operands or memory, and both registers and memory can be symbolic in our implementation of the RISC-V instruction set architecture. And also, this entire SymEx-VP approach is very tightly integrated with the SystemC TLM modeling language I mentioned earlier. And as I said, SystemC models hardware based on the bus abstractions and transactions exchanged over this bus. And so for this reason, the central component of our architecture is this TLM bus. And we have several peripherals attached to this bus. For example, down here, we have a sensor peripheral. And we use a TLM extension mechanism to transport symbolic values over this existing TLM bus. And what this allows us to do is when the software, for example, accesses a register of a UART, like, for example, a data register, then we can modify this memory mapped register in a way that the model returns symbolic values to the software, which are then transported from the model over the TLM bus to the software. And the software would then be explored based on the values that it received from this peripheral. So what we can do essentially is we can inject symbolic values over the peripheral interface, and we don't need to make any modifications to the software in order to inject symbolic values. So we don't need to add any manual make symbolic calls or something like that, but the software is instead explored based on peripheral inputs without any large integration effort on the software side. And yeah, what you see on the left-hand side of this architectural overview is basically standard virtual prototype architecture stuff. And we integrated this with a symbolic execution engine, which is based on KLEE and which provides us with an SMT solver and so on. And essentially, we restart our SystemC simulation for each newly generated input. And for this purpose, I want to briefly expand a bit on our connection with KLEE. So the focus of our work is largely on addressing these integration challenges in the embedded domain, which I mentioned on the first slide. And for this reason, we presently employ rather simple symbolic execution algorithms. And in order to do so, we use a very stripped down version of KLEE without much of the LLVM specific code, since we don't execute LLVM-ER. Similar to S2E, we removed a lot of code from KLEE. And we basically had to implement a lot of algorithms ourselves. So presently, we offer a very simple implementation of concurrent execution or concurrent testing. And our symbolic execution engine is essentially an offline executor which implements dynamic symbolic execution. So we track branches which depend on symbolic values and then iteratively build an execution tree. And when execution finishes, we select a random node from this tree, attempt to negate it, and then receive a new input with which we restart the SystemC simulation. And in terms of memory model, we presently use address concretization. As I said, our focus is more on these integration challenges, and the algorithms for the symbolic execution engine are rather simple at the moment. And we primarily use KLEE as a fancy SMT solver. So we use KLEE's solver interface and SMT abstractions to benefit from all the optimizations pioneered by KLEE in this regard, like the counter example cache and so on. And these algorithms I mentioned are all implemented in a separate library, which we call Clover, which is available on GitHub, and which also includes this stripped down windowed version of KLEE I just mentioned. And one thing that I also would like to talk about a bit is error detection. So since we operate on this low abstraction level and execute RISC-V assembly code or RISC-V machine code directly, detecting errors is of course kind of difficult because we don't have any information about variables and so on. And our work on error detection is largely motivated by the fact that the majority of embedded software is written in C or C++ and has limited protections against these common C pitfalls, right? Like the lack of memory safety and so on. So on conventional operating systems like Linux, you have a lot of mitigations which make it hard to exploit buffer overflows, for example, like stack smash protections, executable space protections, ASLR, and so on. And many of these techniques are not available in the embedded domain. And for this reason, our work largely focuses on finding spatial memory safety violations in embedded software. So buffer overflows, for example, and stuff that you would normally use to do so, like address sanitizer, for example, is also does target more of the conventional domain and also is not as easily applicable to embedded devices. And for this reason, we leverage prior work on hardbound. And hardbound is essentially a technique to achieve spatial memory safety in hardware. The idea is that upon pointer creation, the software has to communicate the bounds of the memory object to which the pointer points to. And then every time the pointer is modified, for example, using pointer arithmetic, these pointer bounds information are propagated by the hardware. And when the pointer is then dereferenced, the hardware can check, in our case, the virtual prototype can check if the pointer is still within the bounds of the memory object to which it originally pointed. And we can see how this works in this example C code. So on line 12, a pointer to buff is created. And then in line 13, we use a LLVM-based compiler pass to instrument the software in a way that it communicates the bounds of this pointer through the special setBound function call, which our compiler pass inserts and which informs the hardware of the bounds of this pointer. And then in line 13, pointer arithmetic is performed, in which case the hardware / the virtual prototype would propagate the bounds information. And when the pointer is then dereferenced in line 13, the virtual prototype can check that it is still within the bounds of the memory object to which the pointer originally referred. And that allows us to check each path enumerated by our symbolic execution engine for spatial memory safety violations. And we then went ahead and applied this technique, our symbolic execution technique, where we inject symbolic values through peripheral inputs, and our error detection technique, where we check each of the paths that we are enumerating for spatial memory safety violations. And we applied this to several IoT operating systems in this embedded domain. So common popular systems in this regard are Riot and Sapphire, which I already mentioned, or Apache NetX. And in terms of tested code, we mostly focused on the network stack provided by these operating systems, because the network stack is, of course, a very complex piece of software with lots of state space and lots of potential for errors. And in this regard, the error detection technique was mostly employed in conjunction with the Riot operating system. And in Riot, we were able to find roughly 13 previously unknown bugs, which were all confirmed and fixed by Riot developers. All of them were previously unknown, and most of them were spatial memory safety violations due to the error detection technique that we are employing. And so for this reason, they're potentially exploitable and critical. And tested modules, which were part of the network stack, which we tested using our symbolic execution engine, were DHCP implementations, DNS implementations, Ripple implementations, which is a routing protocol for this low-end IoT embedded domain, URI parsers, and so on. And I think the fact that we were able to uncover 13 previously unknown bugs in a popular operating system like Riot really speaks to the effectiveness of our proposed approach. And that brings me to the conclusion of my talk. So few key insights to take away here. I think one advantage of our approach, especially compared to the related work that I mentioned in the beginning, is that we have these accurate SystemC peripheral models and we don't need to approximate peripheral behavior. And in my view, this really reduces the integration effort when you want to employ the technique to test a variety of different software like Riot, like Sapphire, and so on, because you can just inject your inputs based on the peripheral interface and you don't need to do any software modifications. And another interesting thing to take away, in my view, is that it was very easy to come up with an implementation of the RISC-V ESA, which allows you to perform symbolic execution, because RISC-V is a relatively simple instruction set architecture. It is modular in the sense that you have different extensions, but the base instruction set of the RISC-V architecture only consists of 40 instructions or so. So it's relatively simple to come up with a RISC-V implementation which executes these 40 instructions symbolically. And then there are several extensions which can be implemented on top, like multiplication, atomic instructions, compressed instructions, and so on. And presently, we support the M extension for multiplications, the A extension for atomic instructions, and the C extension for compressed instructions. And yeah, if you're interested in more information on SymEx-VP and in general our approach on testing embedded software and detecting bugs in embedded software, the source code is available on GitHub. And we have used the source code, which is available on GitHub, as the basis of various scientific publications. If you're interested in more of the scientific perspective, there's an overview publication which has been published this year in the Journal of Systems Architecture, which is called SymEx-VP, an open source virtual prototype for S-agnostic and poly testing of IoT firmware. And the experiments and so on of this publication are also available. So if you're interested in more information in that regard, I recommend you check that out. And yeah, that was my talk. Thanks for your attention. And if you have any questions, I would be very happy to answer them.